Hi, I'm Alex.
I'm Alex.
I'm Jin, and for our project, we did Blackjack.
First, let's go over the basic rules of Blackjack. Before each hand, you have to place a bet, and the bet size for this project will be anywhere from 1 chip to 10 chips. After placing a bet, the player will receive 2 cards face up, and the dealer will receive 1 card face up and 1 card face down. On the player's turn, they can either hit to get another card or stand if they like their hand. The goal of the game is to get as close to 21 without going over, or to beat the dealer. So in this case, because the hand total is 11, the player hits. Now the player has a total of 20, so it would be risky to hit again, so the player stands. Now it's the dealer's turn. Face cards are all worth 10, with aces being worth 1 or 11. So in this case, the dealer has 14 and has to hit, because the dealer always hits when they have less than 17. The dealer got a jack, so now their total is 24. Because they're more than 21, they have busted, and the player wins, meaning they get double their initial bet. There's a lot of extra complicated rules to Blackjack, but that's the basics.
Blackjack is very similar to Pig, in that in both games, the player attempts to maximize their score while avoiding the chance of being punished for their decision. Expectimax, which performs well for the game of Pig, would also be a good agent for Blackjack. We also know that a deck has a certain probability for each card, and that a round of Blackjack will not comprise of many turns, since the player has no actions once their cards sum to 21 or more. Expectimax performs very well for these kinds of games with a small game tree and predictable outcomes.
However, this algorithm has one glaring issue. In Blackjack, if both the player and the dealer bust, the dealer wins, which gives the house an edge of about 2%. So even if we play with perfect strategy, in the long term we're guaranteed to lose money. So we're going to have to introduce some meta knowledge to our agents. For example, what if we knew what cards were left in the deck? This is where card counting comes in. Card counting in Blackjack is actually very easy. What we're going to do is we're going to observe every card as we see it come out of the deck. We're going to use that to update what we call the running count, and then we will use the running count to calculate the true count. And hopefully this will allow us to beat the house. This is what's called the high-low running count, and it's pretty easy. Every time we see a card, if it's between a 2 and a 6, we'll give the running count a +1. And if we see a card that's between a 10 and an ace, we'll give the count -1. In essence, what this does is when the count is high, it means that there's a high number of face cards left in the deck, and when the count is low, it means there's a high number of low cards in the deck. So here's an example of how the running count would update as we see a hand of Blackjack. To calculate the true count, we divide the running count by the number of decks remaining in the shoe. The true count represents how much more likely we are, or less likely, to draw a face card versus a low card. When there are a lot of face cards left in the deck, this is a favorable position for the player. And so what we want to do is bet bigger when the true count is high, and bet smaller when the true count is low. And hopefully we can also use the knowledge of what cards are left in the deck to make better decisions about whether to hit or stand. Because Blackjack is such an easy game, we can make a lot of simple agents relatively easily. For example, the optimist never hits and just hopes that the dealer busts, or the gambler who will hit with some probability, otherwise they will stand.
One agent that would perform well at Blackjack is Tree Search or Expectimax with a dynamic deck. By tracking the exact contents of the shoe, which consists of multiple decks, we can calculate the exact probabilities of seeing each card. Before each hand, we can use Expectimax and the probabilities we calculated to search the game tree and calculate our probability of winning. Using a tree with a dynamic deck will improve our estimates for our win probability compared to using regular Expectimax without keeping track of the seen cards. We can then use the returned win probabilities as a heuristic to decide how large we want to bet. The more likely we are to lose, the smaller we will bet, and the more likely we are to win, the larger our bet size will be. One downside to using Expectimax with a dynamic deck is that we need to update the probabilities for each card every hand, meaning that we have to search a new game tree every time. Compared to regular Expectimax, which only needs to calculate these probabilities once. This method will have to take more time to calculate the odds of winning a hand.
Another agent that should work pretty well on Blackjack is Monte Carlo tree search. A downside of Expectimax is that we have to be very vigilant when we calculate the exact probability that we're going to see every card. If we use simulation instead, we can just hold some object, which is the remaining deck, and then deal cards out randomly. Because Blackjack only has a few actions on every turn, and each hand of Blackjack is only going to go for a couple of turns, we can get a ton of games in a very short amount of time. Hopefully this will allow us to converge to the Expectimax values, but with a much easier implementation.
Q-learning is also a reasonable approach for Blackjack because similar to MCTS, Q-learning is model-free, which simplifies our implementation by using randomness and exploration to deal with this problem. For Q-learning, we're going to represent the states as a tuple of the true count, the player total, whether the player has an ace or not, and the dealer total. To decrease the state space and converge to the optimal policy a bit faster, we're going to make a couple simplifications. We'll divide the true count into 5 buckets and simplify the bet sizing actions by dividing it into betting a small, medium, and or large bet size. The player also has 8 different actions that they could perform. They can hit, stand, double, bet insurance, split, bet small, bet medium, or bet large. This approach is similar to QFO, where we used Q-learning to train an optimal policy and coarse coding to simplify the state space. Deep Q-learning can be better here when the state space is very complex, but because we simplified the game of Blackjack, there's no real need to implement deep Q-learning.
Once we have all of these agents, we can compare them together and see which ones perform the best. An important idea for Blackjack is the idea of gambler's ruin, where a long string of bad luck might cause even the best agent to go broke in a small enough sample. We can also test each of our agents with and without card counting to see how that affects our expected value. In addition, we can also turn on and off the many rule variations to see how those affect our performance.